This is tutorial 6, problem 10.85. The problem goes as follows. If the water surface elevation in reservoir B is 110 meters, what must be the water surface elevation in reservoir A if a flow of 0.03 cubic meters per second is to occur in the cast iron pipe? Draw the HGL and EGL, including relative slopes and changes in slopes. Typically, we don't draw those graphs. We're just interested in calculating the velocities and discharges and elevations. Right, so we're given the discharge through the system as 0.03 cubic meters per second, and we're asked to calculate what is the elevation in surface A. So as you can see, we've got two reservoirs, reservoir A and B. A is the higher one, B is lower, and we've got a pipeline system between them. The first section of pipe is fatter, and it is 20 centimeters diameter, 100 meters long. That goes into a thinner pipe which is 150 meters long, but it's 15 centimeters in diameter. Both are cast iron, so the internal surface of the pipe is quite rough. So if we go look up some properties, we'll see on table 10.4 that the surface roughness of a cast iron pipe, which we can designate as the roughness factor Ks, we can look up on that table and see that it's 0.26. Right, so that's the factor that we're going to use for the internal pipe roughness. Then we look up for water at 10 degrees C. The kinematic viscosity is 1.3 times 10 to the minus 6 on table A5. All right, let's have a look at the solution. So in this system, what we have? We have the water elevation providing energy, potential energy to the system to cause flow from the higher reservoir to the lower. We don't have any pumps in the system, but we do have a pipeline between them, and that pipeline has resistance due to the internal friction between the fluid and the pipe for those two lengths of pipes. We also have the entrance to the first pipe. There's some losses there because it's contracting from the tank into the pipe. Then it contracts again from the fat pipe to the thin pipe. And thirdly, there's a loss where we go from the end of the thin pipe into reservoir B. So there's how many types of losses? There's the entrance loss, there's the friction loss in the first pipe, there's the constriction loss in the center, and then there's the friction loss in the second pipe, and then there's the head loss at exit into tank B. Right. So let's see what we can calculate here. We say that our Ks value, which is our roughness, if we divide that by diameter 20 pipe, that's 0.26 over 200. That will give us a 0.0013 value, which we'll be using later on to look up on one of the tables. So the velocity in the pipe with a 20 centimeter diameter, we've got the discharge, and we can calculate the area, so it's Q over A. The discharge is 0.03, and the area is pi over 4 d squared, and the d is 0.2, because that's 20 centimeters. So that's all squared, and that gives us velocity in the 20 millimeter diameter, 20 centimeter diameter pipe is 0.955 meters per second. All right, so now we can say what is the velocity in the other pipe. So the velocity in the 15 millimeter pipe is Q over A. 15 is also 0.03 over 4, 0.15 squared, and that gives us 1,697 meters per second. So let's have a look at our Reynolds numbers in the two pipelines to confirm if they turbulent or laminar, because we're assuming turbulent flow to get our losses in the pipeline. So let's look at the 20 centimeter diameter pipe first. V over Vd over mu. So the velocity is 0.955. The diameter is 0.2, and mu we looked up for water is 1.3. Kinematic viscosity times 10 to the minus 6. And that gives us a value of 1.5 times 10 to the 5. Let's have a look at the 15 diameter pipe. That's 1.697 meters per second times 0.15 divided by 1.3 times 10 to the minus 6, which is equal to 1.9 times 10 to the 5. Both turbulent. And that is because both of them are above 3,000. Way above 3,000. All right, now we're going to look on the Moody diagram. Remember, the Moody diagram helps us with pipelines to give us indication of the relationship between the friction coefficients and velocities and Reynolds number. So we can then look up our friction coefficient for the 20 millimeter pipe, 0.022. Friction coefficient for the 15 millimeter pipe is 0.024. All right. To do that, we would also need d1 over d2, which is 20 over 15, or 1.33. All right, I think we may be using that for the head losses at the various transitions. So let's have a look at the energy balance in the system. We know that the only thing we have to worry about is the change in height and the losses. There's no pump in the system or anything else producing an energy change. So Z1 is the height at point 1 is equal to the height at point 2 plus sum of all the head losses in the system. So we don't know what Z1 is, because that's what we've been asked to calculate. We do know what Z2 is, that's 110 meters. Now we need to look at all the head losses. So let's have a look at our 20 centimeter diameter pipe. We just take the v squared over 2g term out to the front for ease of calculation. So at the entrance of the pipe, we've got a factor of 0.5, and we look this all up on the table. At the narrowing of the pipe, we get, so this is entrance, we get 0.022 at the 100 millimeter pipe. And that's times 100 meters over 0.2 plus 0.19 at contraction So that is for the 20 millimeter pipe. Now we've got to look, we add on the 15 millimeter centimeter pipe. And yeah, all right, so that was the hundred meters of pipe, not millimeters. Right, so we've got the first term is 0.024 times 150 over 0.15. So that is our friction term for that piece of pipe. Then we have a loss at the exit, 1.0 plus 1.9. So if we calculate that all out, we've got 110 plus 0.0465 times 11.7 plus 0.1468 times 25.19. And that will calculate out Z2 to be 114.2 meters. So that is the height we were calculating. So as you can see, we've got all the losses in the 20 centimeter diameter pipe, which consist of the loss at entrance, the friction loss in the pipe, and then the loss at the contraction. And then in the 15 centimeter diameter pipe, we've got the friction loss, and then we've got the losses at exit. And then we've got the velocity head loss as well, because it goes to 0. Right, so that is then all added up, and it gives us a total head loss 114.2. So the height is 110, so that means we've got 4.2 meters head loss, essentially.